All right, we're going to take a quick look at these two circuits that you dealt with in general, parallel circuit and a series circuit. These bulbs are considered to be in series, and these are described as being in parallel, or the bulbs are parallel to each other. It's just a little bit of weird terminology. If you look at the labels that I put on these, the values that I put on these, you can see that we have 10 ohm resistor or light bulbs or resistors, you could call them even, a 9-volt battery. And I think it's kind of cool to look at these switches when they're open. It has an infinity next to it. It's infinite ohms, which means it's got infinite resistance. And when you close them, they have 0 ohms of resistance. Now, that's not true. That's an ideal situation, but we have ideal switches in this case. You can see right now I have 2 switches closed, but I still don't have any current going through here. And that's because I have this one switch open. When I close that, there will be a current. There will be a current flowing through here because all of the switches are closed now. And you look at the movement of the charges through here, it's pretty slow. And the reason for that is it's a 9-volt battery and there's 30 ohms total of resistance. That's quite a bit of resistance. We can see that if we hook up a voltmeter to this, we've got 9 volts of energy available. And you can see this says positive 9 volts. As a charge goes from here, from the red side to the black side, it gains 9 volts of electrical energy. And if we go like this, from the beginning of the first bulb to the end of the last bulb, we'll have negative 9 volts. So it loses all of that energy per unit of charge as it travels through here. Now, from that, you should be able to deduce the fact that each one of these bulbs is going to have a voltage or a difference in electric potential of negative 3 volts. So each one of these, as I move these from side to side, will have a difference in potential of negative 3 volts. That means that from the side that this red probe is connected to the side that this black probe is connected to, there is a decrease in electric potential. What that means is the charges are doing work. There's a loss of joules per coulomb, and that energy is turned into something else. In this case, it's primarily light, but it's also heat. I don't know if you caught something there when I was moving these probes, but that's a loss of 3 volts. This is still a loss of 3 volts because I've just gone through one bulb and I've gone through this wire. There's no change in potential going through that wire. That wire is considered an equipotential surface. It's got no resistance. There's no work done to move through that wire. If I move to this side of the bulb, though, you can see that there's now a decrease of 6 volts because the charge gained 9 volts here in the battery. The battery did work on the charges. Then the charges do work here, lose 3 volts, lose 3 volts again, and finally lose 3 more volts. And we're back to 0 voltage or 0 energy. And you can see that I could slide this around anywhere and I'm going to be at negative 9 volts. The charges basically don't have any energy left. They shouldn't be able to move through these wires. But because we call these wires ideal and we pretend that they have 0 resistance, you can see that we have a change of 9 volts to the end of this battery and nothing after that. When you look at the current throughout this thing, hopefully it's pretty obvious to you that if you hook this up, you're going to have the same current everywhere because there's never a split. There's never a branch. This is always 0.3 amps. And the way that you would calculate that is to use Ohm's law, which says that the electric potential, the voltage available, is equal to the current times the resistance, or the current is going to be directly proportional to the voltage and it's inversely proportional to the resistance. Big resistance, low current, big voltage, big current. So anywhere I move this thing, we get 3 amps. Now, if I open one of these things, doesn't matter which one, there's no current flowing through any of the circuit. There's just no path for the electrons to move, for the charges to move. So the current immediately goes to 0. We'd still have a potential difference, though, if I open these switches. So there's our electric potential here of 9 volts. If I open a switch, there's still a potential of 9 volts. And there will be the whole way around here now. I go to this side, you can see that it's still a 9 volt difference in potential. But here it gets interesting. There's a 0 potential difference in this wire. And the reason for that is that all of this section of the current of the wire is at the same potential. It's at the potential of this end of the battery. So everything over here is at an equal potential. It's all at zero. Right? There's no electric potential here anymore. Over here, at the positive end of the battery, same thing. There's no electric potential. There's no difference. There's no reason for charges to move. Everything in this side of the branch is at the same potential. There's no difference in potential between these 2 points. The only way to get a difference in potential is to go from one side of the switch to the other side, which is basically like connecting from one side of the battery to the other. Okay, so that's our series circuit. Parallel circuit, a little bit more involved. You can see I have 3 switches in here. The voltage available, again, is going to be 9 volts to start out with. So I can put this on here and I can measure 9 volts. So we have 9 volts of energy per charge. I'm immediately going to put this on here, and this is going to measure the total current. Right? That's a total current. It's not going to be the current through each one of these branches. It's going to be the total current. What I'm going to do is just close one of these switches. You see that bulb lights up. We have a current of 0.9 amps and a voltage of 9 volts. And that kind of makes sense because we could say, again, the current equals the voltage, 9 volts, divided by the resistance, 10 ohms. So we have a 0.9 amp current. Now, this is where things get interesting. Normally, you would think, oh, by the way, if we gain 9 volts here, we're going to lose 9 volts here, negative 9 volts there. Now, when I close this other switch, something interesting happens. You would think, oh, there's going to be more resistance, so there's going to be more less current because there's more resistance. In this case, there's actually less resistance overall. And the reason there's less resistance overall is because now there are going to be multiple paths for the electrons to travel through. So there'll be less resistance overall. So watch how the current increases when I close that. It doubles. It goes to 1.8 amps instead of 0.9 amps. And the reason for that is we have current through this branch, right? The lower branch. We now have current through the middle branch. And because this entire side, right, this entire side of the circuit compared to this entire side of the circuit is a difference of 9 volts. There's a 9 volt loss in energy. And it doesn't matter if you connect there or connect right here. There's a difference of 9 volts, whether the switch is open or closed. Right? I can open or close these switches. Basically, these sides, when the switches are open, are just extensions of this end of the battery. And the right-hand side is an extension of the other end of the battery. That's all they are. So each one of these is going to have an electric potential of negative 9 volts. Right? So I can put that on there. Now, if I slide this to this side, it's going to be 0 volts. Now, there's a light bulb there, right? And you'd think there might be an electric potential there, but there's not, because this wire is just a complete extension, right? The bulb is part of the wire. You can see there are electrons in there or charges in there. So if I just extend this all the way back, it connects to the battery. So everything in there is at the same potential. If I touch this anywhere here, I'm going to get 0 volts. Anywhere along that wire, anywhere, right? It could be 0 volts. It's not until I go to the other side, right, on the other side of these switches, that I get that difference in potential. And when I close the switch, nothing changes really. The only thing that changes is current's allowed to flow, right? Still a difference of 9 volts. Here, there's still a difference of 9 volts. I'll close that switch and we'll get increased current. We need to check something out with these bulbs too, though. Check out the brightness in the bulbs. Right? When I open and close the switch, the brightness in the other 2 bulbs does not change at all. The reason for that is that they still have 9 volts of potential difference. They still lose 9 volts when the charges go through there. This is something that confuses people a lot. They say, okay, oh, there's 9 volts of potential for the first bulb, 9 volts of potential in the second bulb, 9 volts potential energy drop in the third bulb. That's 27 volts. That's not the way it works. You have to consider what one charge would do. One charge wouldn't go through all 3 of these bulbs. One charge would go through one bulb and lose 9 volts and go back to the battery. Another charge will go through this bulb, the middle bulb, lose its 9 volts and go back to the battery. Over here, it's a different situation. A charge has to go through all of these bulbs. A charge has to leave here. It has to go through the first bulb, the second bulb, and the third bulb. If it lost all of its energy right here, if we had a difference in energy of 9 volts in this first battery, there'd be no energy left to make it through the other 2, the first bulb. There'd be no energy left to make it through the other 2 bulbs. So there's a difference of 3 volts, then another 3 volts. And then here, when we're finally at the end of the circuit, the charges end up with 0 electric potential. I hope that was helpful. You can watch that as many times as you want. That's the general idea behind series and parallel resistors.